Okay, Ellie, you just left. Here's 4.2. We're going to start this guy, but I want to like kind of preface this and talk about the next couple sections. 4.1 that we just got done with was the section on inverses. You don't have to write this down if you don't want to. 4.2 is exponential functions. Do you know what an exponential function is? Like if you graph it? Like, nope, x to the third is like a polynomial. It would be like 3 to the x power. Right, where the exponent has the variable, right? X to the third power is just a cubic function, okay? So this is a polynomial where this is an exponential function, so not exponential. But if you graph him, he looks like, whoop, one of those, where he goes up like really fast. He's not, let me draw it better, whoop, like that, right? Exponential growth. Or sometimes it could be exponential decay where it's going like this. We'll get to that, okay? And then section 4.3 talks about log functions. Okay, and a log function, when you graph it, looks like this, okay? So a little bit similar to exponential functions, kind of ish, but why? Why like these three sections? What the heck? Why inverses and then all of a sudden we do exponential functions and log functions? Like what?
Because they want us to start doing trig.
Not quite. We will get to trig though. Exponential functions and log functions are inverses of each other, right? An inverse means to undo something, right? Like, so x squared, the inverse of x squared is the square root of x. The inverse of the cubic root of x is x cubed. What's the inverse of a linear function? Another linear function, right? Okay, so those are inverses of each other. They undo one another, but exponential and log functions undo one another as well. So that's why we learned inverses, and now we're doing exponential and log functions. Okay, so for example, I'm going to go down. Don't write anything. I'm just going to go down just to preface this. Okay, so when we're talking about, I'm going to go not compound interest. I'm going to do this one right here. Do you guys know what PERT is? Yeah, so like PERT is like continuous compounding interest, right? Okay, so I skipped really far down. You don't have to go to this, just watch, okay? So this is like, let's say I'm given $100, right? And $100 would be my principal, right? E is just E. E is a number. E is a number in your calculator, right? My interest rate is like 5%, okay? So let's say 0.05, okay? Sometimes they will ask you the question rather than giving you an amount of time, like after 10 years, how much is it worth, right? Sometimes instead of saying that, they will say, how long will it take before that turns into $600, right? Okay, how long will it take? And in that case, you're solving for t, but how do I get t out of there because it's in the exponent? You use a log to get it out, right? This is an exponential function. The t is in the exponent. So we have to have logs and we have to have inverses in order to be able to undo that function to solve for t. Does that make sense? So that's what we've got going on here. Okay, all right, let me get actual to the examples here. Exponential functions here they have, just to start with, like they want us to plug in 2 to the x power. I'll come back to this here in just a second, but they have 2 to the x power. They want us to plug stuff in. Do you know how to plug this into your calculator? They want us to plug in -1. So this is like 2 to the -1 power. Okay. 2 to the -1 power. What do you do with negative exponents? Like, how do you turn your negative exponents positive? Do you remember? I'm going to tell you, and you're going to be like, oh, yeah, that's right. This is a fraction is over 1, right? Yeah, if I want this exponent to be positive, I'm going to bump him down to the bottom, right? So this will be 1 over 2 to the positive first power, or just 1/2, right? That's how you deal with a negative exponent. So -1 is at 1/2. All right, I'm going to go over to the graph because I've given you the graph. -1 is right here at 1/2. You see that? Okay. If I plug in 3, this is like 2 to the third power. What's 2 to the third power? 8. Okay. So 3 is at 8. 3 is at 8. Oh, they don't have it on the chart right here, but it'd be right there. 3, 8. That's what he would be, right, on the graph. Okay, if I plug in 3, I get 8. If I plug in 5 over 2, 5 over 2 is 2.5, right? So this would be like 2 to the 2.5 power. What does that come out to be? 2 to the second power is 4. What? 5.65. Okay, so if I do 2.5 would be here. He's up at 5.65. So 2.5 comma 5.65. Does that make sense? We plugged in 2.5. Okay, if you plug in 4.92, 2 to the 4.92 power, 30.27. So if I would go all the way over to 4, this is 3. 4 would be right here. 4.9 would be here. He's all the way up here at like 30 something. Bleh, all the way up there. Okay, so we can see how the larger numbers I start to plug in, he starts to go up really, really fast, okay? So this is an exponential function. This is 2 to the x power. It's an exponential function if the exponent is the variable, right? The x has to be up here in the top, not down here like x squared. That's a polynomial function, not the same thing, okay? Now, every single exponential function, let me go down here to this graph right here. Every single exponential function, like 2 to the x power, every single exponential function will cross here at 1, okay? Look at this coordinate right here. Circle him, 0, 1. 0, 1. If I plug 0 in, what's 2 to the 0 power? What's anything to the 0 power? 1. Anything to the 0 power is 1. That's why if this was 3 to the x power, or 7 to the x power, or 100 to the x power, he would still cross here at 0, 1, because if you plug 0 in, you're going to get 1, right? Anything to the 0 power is 1. So he's always going to cross there. Okay? I say that, but like if we do this, that's not going to cross at 1 because we've shifted him up 4. Does that make sense? Okay, so we'll start to do that stuff to him. But if you have just a regular exponential function, he's always going to cross at 1. And then he'll go like this, okay? That is the same thing for, if you go to the right side here, this is 1/2 to the x power. And that is an exponential decay function. If you want to put that up here, it probably says it, but let's make it big. This is a growth function, and this is a decay function. Okay, so he's going downhill from left to right, but still crossing at 0, 1, because if I take 1/2 and I plug in 0, anything to the 0 power is 1, right? Okay, now, how do I tell by looking at the equation, like 2 to the x power versus 1/2 to the x power, whether it's a growth or a decay? How do you know? Whether it's a growing function or a decaying function. Like example 2, is that going to grow or decay? How do you know? Because it's 1/5, right? And 1/5 is a fraction. Okay, but be careful when you say fraction because this is a fraction as well, and that's going to grow.
Less than 1.
It has to be a fraction less than 1. Yeah, you're right. You're right, Matthew. But fraction less than 1. Okay, now if it's a number larger than 1, it's going to grow. Now, what happens if I have this? Let's say I have 7 and I have 1/5 to the x power. Is that going to grow or decay? Because this is a number bigger than 1, but this is a number less than 1. So is that going to grow or decay?
It's going to be 7.
Let's say if I plug 1 in here, right? This would be like 7 times 1/5 to the first power. If I plug a 2 in there, that's 7 times 1/5 to the second power, which is like taking it times 1/5 times 1/5. If I take 7 times 1/5 to the third power, it's 1/5, 1/5, 1/5. Is that making it bigger or smaller? Smaller, right? The 1/5 is the part that is being like taken multiple times. So we don't look at the 7, we look at the number that we're taking the value of, like to that power, right? So this is going to be a decay function. Don't even look at this number, right, to determine growth or decay. Okay, let's talk about domain and range. Let's just do this problem. So 1/5 to the x power. I'm going to plot points. Typically, I don't like to do that, but I'm going to plot points, okay, until we get used to this. So let's go, I'm going to go, I don't know. Let's go -2, -1, 0, 1, and 2. Okay, those are the guys that I want to do. All right, I'm going to start at 0. If I do 1/5 to the 0 power, what's that come out to be? 1, right? So 0 is at 1. I'm starting in the middle of my graph, okay? If I do to the first power, 1/5 to the first power is 1/5 as a decimal. That is 0.2, okay? If I plug in 2, what's 1/5? 1/5 to the second power. What's 1/5 to the second power? What's 1 squared? What? 0.04. 1 squared is 1. 5 squared is 25. So it'd be 1/25 or 0.04. Okay, now let's go -1. All right, ready? -1. 1/5 to the -1 power. How do I get that to be a +1 power? Flip it, right? It'd be 5 over 1 to the positive first power, so this would be 5. What's -2 power going to be? 25, right? Okay, so we've got something that's starting up really high and it's decreasing. So if I do the graph of this guy, whoop, okay, I know he's touching at 0, 1, so I'm going to plot that point. He is like -2, all the way up there. I don't know, -1 is at 5. 1, 2, 3, 4, 5. I'm not even on the chart. Like this guy's not even on the chart. 1 would be at 0.2. This guy would be at 0.25. He's doing one of these. And he's leveling out. Okay. Now, you know last chapter when we talked about this little dotted line? What's that thing called? Because he's not going to touch that line. That's your horizontal asymptote. He will have a ha. He will not have a va, but he will have a ha. He's going to level out at that point. Okay, so we got to do domain and range. Domain, range. Domain is left and right. Will he go to the left forever and to the right forever? Yeah, even though this one's going up, he's going out as he goes up. So domain is all rails. Range. Greater than 0. So I'm going to say that y's are greater than 0. Will he touch 0? No, because that horizontal asymptote's there. If you want to write it in interval notation, you could go 0, infinity, paren, right? Like that's another way of writing that. However you want to do it. I don't know which one you prefer, but there's that. Domain, range. Got it? This is an exponential decay function, right? Decay function. Okay. All right, here we go. Graph each function, show the graph of 2 to the x power for comparison. All right, so I'm going to go 2 to the x power over here, like just the main one. 2 to the x power. We know he's going to hit at 0, 1, right? What's 2 to the first power? Like if I go over 1. 2 to the first power is 2. What's 2 to the second power? He's going to be up at 4, and then he's going to go downhill from there, right? Like he's going to do one of these. Something like that, right? That's what he'll look like, okay? That's what normal 2 to the x power looks like, okay? When you graph these, I am not very particular, okay? What's the negative right here going to do to him? What does a negative normally do to him? Flips him over which way? Over x. So I'm not very particular. I do know one point, though, that he's going to touch. Normally he touches right here at 1. He's going to touch at -1 right there. So he's going to go like this. I'm not very particular. Okay, he's going to have a horizontal asymptote. Looks like that. He's over x. Okay, what does this 3 do on part B? Nope. Up 3 would be 2 to the x plus 3 over here. So this guy is kind of like he's in parentheses right here. So it's not up. What'd you say? No. He's going to the left 3. Oh, yeah, sure. The 3 is going to the left 3, right? So normally he touches here at 1. I'm gonna get rid of that line. I'm gonna move him here. Okay, normally he's here at 1, right? But I'm going to the left 3. 1, 2, 3. So now my dot is here. I still have a horizontal asymptote here, and he's going to go like this. I've just moved him to the left 3. That makes sense? That was really quick. Okay. What the what? Oh, man. C. What's happening to C? Nope.
Right.
He's right 2. Right? Because right means negative. Okay, right, and down 1. Right 2, down 1. Okay, so that normal spot, yeah, I'll do that right there. That normal spot that's at 0, 1, he's going to be right 2, 1, 2, and down 1. This dot's right here, right? Where's the horizontal asymptote going to be? Like my horizontal asymptote's usually, yeah, just down 1 lower, right? So he's going to be here. And my thingy thing is going like this, like that. Okay. Good. The only thing that moves your horizontal asymptote is the down or up part. Left and right's not going to move your horizontal asymptote. Does that make sense? Only the up and down part. Okay, and I'm not very particular. Like, look at my graphs. They're not real great.
Is the horizontal asymptote just -1?
Yes, yes, correct. He's just here at -1. That's the only thing that moves your horizontal asymptote is when it goes up or down. Left and right doesn't move your horizontal asymptote. Okay?
Could you have it refrigerated?
You could. And like plot points and stuff. Sure, absolutely. Yeah.
Because that doesn't make any sense to me.
This doesn't make any sense to you? Graphing? Yeah. It's kind of a beast. We didn't do domain and range. Domain, range. Crap. Go back to A.
All real
Domain is all reals. Range?
greater than 0.
Less than 0 because he's below. Below the asymptote, right? Less than 0.
I was looking at that.
Oh, sorry. This one right here. Okay. Domain? B?
All real.
All reals. Is it always all reals for an exponential function?
Nope.
Yep. Range? Y is
Greater than 0.
greater than 0 still. Yep. Domain? For C? All reals. Range?
Greater than -1.
Greater than -1. Awesome. Yep. Okay, good. All right, let's do like 4 and 5, and then we'll quit. Okay?
Greater than -1?
Greater than -1. -1 is where your asymptote's at. Okay, let's do 4 and 5. These are my favorites. I like these so much.
So you like switch it around?
Yeah, well, kind of. No, not yet. Not yet. We're not getting to that yet. Okay? They're wanting to solve for x. Like I have to get x by itself. Okay? Now, these guys, these are my favorite. They're like little puzzles. Okay? So if I look at this side, 1/3 is my number. If I look at this side, 81 is my number. Okay? What I'm trying to do is I'm trying to get those to be the same number, right? Okay? So I know that 1/3 is like saying 3 to the -1 power. Does that make sense? 1/3 is 3 to the -1 power. Okay, what's 81? 3 to the 4th power? 3 to the 4th power, right? Okay. All right, now, I got to have this x go somewhere, right? Like, that was a part of the original part. Oop. So, 3 to the -1 power is just taking the place of 1/3. Like, this guy is getting replaced with 3 to the -1 power. There's still an x there. You see that? This is what's called the change of base. Like, you're changing the base on both sides, right? Yeah, we did. Yeah. So, here's the fancy deal. If I have this going on, like, how do I combine those two? Yeah, he's just -x. We're just multiplying, right? So that's like saying 3 to the -x equals 3 to the 4th power, right?
So it's
Now that they're both 3's, I can cancel them out. -x equals 4. And if I divide by -1, x is -4. Make sense? Yeah, kind of ish. A little bit. Okay, same thing for example 5. I look at my two bases. My two base numbers are 2 and 8. Can I make those to be the same number? Yes. What are you going to change them to?
the 2.
Yeah, this guy gets to stay. He can stay 2 to the x plus 4 power, right? But 8 is going to switch. 8 is what? 8 is like saying 2 to the 3rd power, right? Like 2 to the 3rd power is taking the place of the 8, right? Okay. Do we see what's going on? Okay, so this left side, he's just chilling the whole time. Equals, if I distribute that 3 through, don't forget to distribute through the whole thing. This is 2 to the 3x minus 18. Yeah? Do you see how that works? It's kind of like a puzzle. You try to get them to match on both sides, right? Okay. This 2 cancels with this 2, right? Since they're both 2's now. And then you just have a math problem. X plus 4 is equal to 3x minus 18. Okay. What shall we do?
Minus the x.
Minus the x,
Plus
okay,
18.
plus the 18. 18 plus 4 is 22, equals 2x. So x is 11. Beautiful. You see how that works? You're just switching both sides, trying to get them both to match. Okay? A little bit different for number 6, but we'll stop there. Okay? Good? Happy with that?
Yeah.
That should be able to get you a little ways. Yep. Okay. All right. Goodbye, Ellie.